Hello, good morning, good afternoon, and welcome wherever you are joining from around the world. We have a large number of people on the webinar today. We're really excited here because it is Tom Prevost, Tom Prevost's final webinar for Weidmann. Good morning, Tom.
Good morning. How are you
So Tom,
today, Frankie?
yeah, well, first of all, for old time's sake, I've left the donkey behind me, Tom, for you. I know it's your favorite here in my home office, which I normally get rid of for our webinars. But as today we are a little bit more casual than usual, hence your awful shirt there, Tom. Then we will run it a little easier today. First of all, thank you very much for all your questions already. We received a lot of questions. I'm sure we're not going to get to go through them all today, but even in Tom's retirement, there will be people at Weidmann that can still answer those questions, and also Tom will be, no doubt, hanging around the peripheral for a little while. He can't let go of his transformer roots that easily. So Tom, before we dive into, one other thing, if you would like to ask questions, just in case there is something that is absolutely burning or you want to make a comment, you can click on the question box, which is a chat box with a question mark. You could dive in there and type something in, and I will try to keep up while Tom's answering some of your questions that we've already received. But before we get started, Tom, clearly you're not in your log cabin in Vermont. When did you retire and where are you at the moment?
So it's a little convoluted on my retirement because I actually retired on March 1st, but since that time I've spent a week in Istanbul and another week in Denver for some company meetings and then an IEEE Transformer Committee meeting. But you're right, this is not my log cabin. This is a little camper that my wife Rosie and I pulled down to Florida. We had an opening in the snowstorms up north to allow us to get out, and I had to get out. It's what I call mud season in Vermont right now, which is the worst time of the year. So everything's melting, and it's time to get out of Dodge.
So
So
you're a real retired person now, heading to Florida when the mud season and the snowstorms come.
hence the shirt, right? Hence the
Yep.
shirt. I wear this every day.
Okay, well, look, I mean, just a couple of things. First of all, I want to point out to our listeners that today we gave Tom a lesson in PowerPoint, and he found a new way of sharing his screen, which is a little bit too little too late, Tom, for you, I guess. There's not going to be so many PowerPoint presentations, but I'm glad we worked that out for everybody joining us on the webinar today. And
Yeah, let's hope it works.
yeah, and we're hoping that your internet connection stands up. How are you? How's your Wi-Fi, Tom, in your camper van?
Oh, I have a wonderful Wi-Fi. One of the things that I got from my camper was a Starlink system, so I can pretty much get internet anywhere I want to go. Yeah,
Big thanks, of course, Tom, to your friend Elon Musk, right?
yeah. I haven't. I've been a little worried about the protesters outside my camper since they saw the Starlink antenna sticking up in the air. Yeah.
Just put some tape over it. It'll be fine. Well, look, as nice as it is to chat to you, there's a few people on here that want to try and tap into some of your wisdom in these final hours of your Weidmann career. So I have a lot of questions to try to get through. So I'm going to start with an easy one for you, Tom, because I think
Okay.
this is one that even I've heard you answer a few times. But I will start with insulation life versus temperature. And I have for you, what is the theoretical increase in life of a transformer if we use 130 degree C thermal class insulation, but operate at 110 C hotspot? And C, Tom, is Celsius, right? Not Fahrenheit.
Thank you for pointing that out.
No, no problem.
Um,
American.
Yeah, insulation life and full transparency. I did see some of these questions and especially this one because it's really pertinent, as Francis said, to a lot of questions that I've answered or been involved in over the years. So I did present a couple slides. So I will share my screen. Okay, so do you see this slide?
Yep, we can see it, or
Francis?
at least
Okay,
I
all
can.
right. Oh, to answer this question, unfortunately for the industry, there's two what we call loading guides. There's one in the IEEE world and one in the IEC world. In the loading guide, if you're a transformer operator and have any questions or want to learn more about transformer life versus loading, then you need to read these guides from cover to cover. But basically, there was this guy named Arrhenius at the turn of the century, the last century, that developed this life curve that's been adopted by the industry that basically relates life to temperature. And these constants, A and B constants, are based on the material. So when you develop a new material, there's an IEEE standard that allows you to do some thermal aging tests that give you these new constants. And these constants will allow you to calculate what's called the per unit life. So per unit life is again defined, a per unit life of 1 equals a life of 180,000 hours. That's just over 20 years. So if you load a transformer continuously at the rated temperature, it should last for 20.5 years. Sorry about this, but this comes from another guide, which is high temperature materials, which show you that if you have other insulation systems that are higher temperature, then you have new A and B coefficients. And there's a whole lot of discussion about whether you maintain the B, which is the slope of the curve, or not. But based on these formulas, you can have different life curves. So I pulled this life curve from this same standard 1276. It's an example that's in one of the annexes, but it shows you a life curve of an aging acceleration factor versus what the hotspot temperature is. So if we're talking about 130 degree insulation material, it would have an aging acceleration factor of 1. Now, to answer this question, if we use the same curve and say that my hotspot is really going to be only operated and limited to 110, then I can see that my aging acceleration factor is somewhere about 0.15. So that's about between 6 and 7 years longer I'm sorry, 6 to 7 times longer than what the life would be at 130 degrees. Now, if you take that 6 times 20 years, that's 120 years. This is all theoretical, but based on the insulation and the formulas there, that's a long answer to the question. If you operate at 110 continuously and you have a 130 degree system, it's going to last for 120 years, according to everything in the loading guide.
Okay.
How's that?
Yeah, it was good. Good. I mean, I think that's an easy one for you. But
Well, yeah,
let's go ahead.
the key point to that is that this is the loading guide. It's theoretical, and it's also based on the insulation life. So the transformers really last 120 years. Probably something else is going to happen. And you have to look at the auxiliary equipment. You have to look at the bushings, for example. But yeah, it's pretty much if it's designed for 130 and you're going to operate at a lower temperature, it's going to last significantly longer.
So did you base, Tom, your length of career at Weidmann on one of these aging guides, or?
Absolutely, absolutely. My aging factor is about 0.185.
0.185. Okay.
Yeah.
Does that include your short break with the Austrians?
Yeah, that increased it by another factor too. So that was a good one. Yep.
Okay, good. So another easy one, because this again is one of your favorite topics and certainly one of mine, as you know. So it's a question on design curves, and specifically, are Weidmann curves for oil channels with stands still valid? Any update due to new oils, press boards, and investigations? And when we talk about the Weidmann curve, Tom, we mean that straight line that you usually show.
Yep. Yeah, I've got the curve. I think I have it here. Just um,
And just
so
for
I
those
pulled.
asking, sorry, Tom, we will share the presentation and documents afterwards. Yes.
Okay. So I pulled these curves. In a lot of the answers I'm going to give, I try to use references and name the reference. I forgot to put it here. But this actually comes from the Weidmann Transformer Board 3 book. It's a reprint of the curves that were originally published in the original Weidmann Transformer Board book, which was published in 1978, 79, I'm sorry, 1979. So the question that was asked, I think, was, are these still applicable? Number one, for mineral oil, and are they applicable for alternative liquids, right? Other liquids that are being.
Yeah, we did have a question later about whether we have design curves for ester and other
Okay.
liquids. You
All
can take
right.
that, Tom. Yep.
Yeah. So, in fact, what Weidmann has not changed these design curves since they were originally published in 1979. Um, what what we have done is further validated these curves, and they have really become the de facto industry standard. Many transformer manufacturers use these curves as a reference, and also consultants and other insulation designers. Um, what Weidmann has done to further improve design technology is more on how to adapt these curves to, because these curves are really based on two-dimensional analysis. So it would be a line along a surface of insulation. What we're developing now is more, we've moved into the 3D realm, and we're looking more at volume effects and how we can transfer a volume based to back to these two-dimensional lines. So there's a discussion of that in Transformer Board 3. Several papers we've written in that regard as well. But the more research that we're doing now is more in the 3D realm on how we can look at volume effect versus the simplified two-dimensional analysis. In regards to alternative liquids, these curves are, as it states there, for mineral oil. We are currently developing curves for ester liquids. We have design criteria that we're using, but we also have two extensive high voltage labs in the Weidmann global footprint. One in Rapperswil, Switzerland, and another one in St. Johnsbury, Vermont. And so we have a large research project now where we're doing a lot of analysis on both natural and synthetic ester to further develop and see how these curves either apply or need to be modified for alternative liquids.
Okay, and we had a question come in while you were speaking there. It says, could you tell us the low probability described? Is this for disruptive discharge or PD inception? Is this 1%, 5%?
Oh, I don't know if
Thanks,
it's a,
Hitachi Energy.
so yeah, these curves are 1% probability of partial discharge inception. So, and it would be a PD inception. Obviously, in the laboratory, we have PD inception capability down into the digit picocoulomb range, 1 to 3 picocoulombs. And then in a factory, this would be, whatever the factory could get to, probably 10 to 30 picocoulombs, hopefully. But yeah, it's PD inception to whatever level you can measure and 1% probability. And typically we do that with a Weibel distribution.
Thanks, Tom. And of course, it wouldn't, Thomas, be a Weidmann webinar without a correction from our good friend Chris Krauser.
All right.
Thank you, Mr. Krauser. I think you all know Chris as a Weidmann employee of past and still very active. He suggested that you were wrong, Thomas. The curves are not along an insulation surface. The curves apply to oil gaps. So just a correction there.
No, thank you, Chris. You're absolutely right. They apply to oil gaps, right?
Perfect. Thank you very much, Mr. Krauser. And following on from the design curve question, so do you have a recommended curve showing the withstand voltage of paper in an oil immersed system versus thickness, and the same for transformer board?
So the short answer to that is no. The insulation criteria for paper insulation versus thickness is more a reflection of the manufacturer themselves. The development of those curves are typically proprietary to the manufacturer. When we look at insulation board, if we look at these curves, we're using the board, the solid insulation, to divide the oil into smaller and smaller oil gaps. The oil is the weak point of the oil press board barrier system. So the press board essentially only needs to be thick enough to be able to divide the gaps and maintain consistent clearance. Even 1 millimeter thick is adequate for the thickness of the board because it's so much stronger than the oil. So there's no specific design criteria for thickness of board versus the dielectric strength of the board itself, because the liquid, the oil, is always the weak
point. Okay, thank you, Tom. Well, we're going to switch gears to another topic of yours that I've heard a lot about, and that's impact of moisture, of course, on our material. And the first question I had for you there that came in is IEEE incorporating moisture in the calculation of the transformer life, as IEC did? Now, I have a hunch that you asked this question recently in Denver to try and provoke a response. So I would like you just to explain to us what that means, what the answer you got in Denver was, if that's all right, Thomas.
Yeah, actually, so in Denver, which was 2 weeks ago, was the IEEE Transformer Committee meeting. And during that week long of meetings, there's all sorts of working groups that meet to discuss revising IEEE transformer standards. And one of those standards is the loading guide. And the loading guide in IEEE is called C5791. Dave Wallach from Duke Energy is the chairman of that group, and he's leading a revision effort right now. And so yeah, I asked Dave. Dave said that he wasn't complete with his revision cycle because he was waiting for the moisture guide, which I am chairing, to be complete. So I said, Dave, does that mean that you're finally incorporating a moisture criteria into the aging life of the insulation? And he said, no, we're going to do that next time. So then I said, so why are you waiting for me? And then he just smiled. So I'm going to share some slides here again to show you, I think, what the, oops, sorry.
By the way, I just want to comment and thank everybody for joining. Tom, you'll be pleased to hear that for those listening, we had a bet before the webinar, and I just won the bet for the number of people on the line. We had more than 400 registrations, and we have a lot of people with you. So you're certainly still popular, Tom, even in your old age.
Oh, good.
And you owe me a beer as I won the bet.
So, all right. So this is what the question was about. So if you look at this, and if you remember the Arrhenius equation that I showed earlier, that showed the light is what was added in this Annex A for the IEC loading guide is this A factor. And this A factor here is a pre-exponential factor, which is what it's called. But the A factor then is given in this table. So if we look, depending on the paper, we can see a different A factor for different levels of moisture content. Now, I'm going to talk about later probably a CGRE working group that was just completed that is called condition of insulation when the transformer leaves the factory. And one of the largest conclusions from that working group is that the moisture content of the insulation needs to be 0.5% or less. So in that case, it's consistent with this column here. So this column would be the factor for insulation that is already in the standards. These values, either 1.5% or 3.5%, would be acceleration factors given the higher moisture contents. So in this annex, there's data that can support development of this A factor. So what comes back to what Dave Wallach was talking about from Duke in chairing the IEEE meeting was that this moisture content is the moisture of the insulation at the hot spot. So the hot spot is deep inside the winding, and it's very, very difficult to measure. So when both the IEC and the IEEE attempted to put a factor into the loading guide to show how the aging is accelerated by the moisture, we needed to somehow have a way to measure that moisture in the hot spot, which was how the working group, it's called C57.162. It's an IEEE guide for determination of moisture and insulation. That is one of the working groups that I'm chairing, and hopefully we'll publish this year, which gives you guidance on how you can determine the moisture at the hotspot. So hopefully once that's published, then Dave or who else takes the realm in IEEE will, on the next iteration, be able to incorporate a constant for moisture in the aging equations. It's a long answer, but it's been a long process because we really, in IEEE, wanted to incorporate a moisture factor into the life curves, but needed to figure out how to measure it.
Yeah, normally everything's so fast in IEEE, right? So it comes as a surprise. Yeah.
Yeah, this moisture guide's been going on for 10 years. So, yeah.
Did you have hair when it started, Tom?
No, but I had more hair than I have now.
Okay, well, enough teasing. We did have a quick follow-on question from that from an industrial transformer operator in Brazil, and it was just I don't want to say a quake, but it was about aging. And could you say something in relation to aging process on GIS connected transformer insulation? I'm not sure if that's something you can answer quickly, or whether we need to take that one offline.
Yeah, I don't have any curves or data to refer to for that, but I can say that if you have transformers that are connected to GIS systems, they tend to be more impacted by the switching impulses that are coming from the GIS. So as a lot of the transformer design in the past has been and protection has been more looking at traditional like oil circuit breakers that tend to be slower in nature. So the GIS can give you impulse surges that can resonate in the transformer and cause premature dielectric failure. I don't know if that's what the caller was talking about, but I can say that at the next Transformer Committee meeting, we have 2 tutorials at every meeting. I'm actually in charge of these tutorials, and Jim McBride chairs a group which is looking at transformer and breaker interaction, and there will be a tutorial on that. So if the caller is interested in that, then yeah, he can attend the meeting or give me a holler and I can give him a copy of the presentation.
Thanks very much, Tom. That's great. And we did have a question on aging about what is the shelf life of craft paper, which came out of nowhere. And I would like to direct you to the Weidmann Electrical website, where there's a whole document on shelf life of materials and how to store and protect those materials to get the most shelf life you can out of a product. Tom, I'm going to shift gears here because I know this is a topic that both of us like and I finally understand. For those that don't know, the one thing that I have thoroughly enjoyed working with our Weidmann engineering team, and I extend that to others, but specifically to Tom, is my education about transformers. So even for the simple marketing guys, Tom takes the time and really, I don't want to say dumbs it down, Tom, but I guess that's the term you'd probably use to describe some of these answers and information. And one of the things I learned recently is about impregnated and not impregnated vapor phase processes. And the question is there one in favor to another and why? I will let you answer it, Tom, but yeah, I appreciate you very recently educated me on this topic.
Yeah, thanks, Francis. It's yeah, it's too bad I'm retiring because I think it would be a life project educating you on transformer insulation topics.
Quite possibly.
But
Yeah.
I think you understand the term relative permittivity now.
I
So
do, and I was very disappointed that not a single question came up on relative permittivity, as that is one of the few things you achieved in my education last year was teaching me about that. So, but all I can say is for your barriers, I recommend buying low density board. Yeah, Tom, over to you for the question on impregnated and non-impregnated material in the vapor phase process.
Okay, so as I understand the question, so when a transformer is manufactured in the factory, one of the key important things, and I already mentioned this from the Seagray work, was that the insulation, the cellulose insulation, needs to be very dry. And I know there's discussion currently going on in the IEC standards world where the primary IEC standard IEC 60076-1 is considering putting in the standard itself a minimum amount of moisture that or maximum amount of moisture that the transformer has to have in it, which will be, again, this 0.5% moisture content. So how's that done in the transformer manufacturer? Typically, especially for large power, they use what's called a vapor phase system. So it's a vacuum chamber where you can heat up the transformer core and coils, and then you use kerosene vapor as a heat transfer mechanism, and then you use vacuum to remove the vapor. And it's very, very effective. Most large transformer manufacturers use this process. What's different and what the question is about is that some manufacturers at the end of the vapor phase process, because it's in a vacuum chamber already, they will introduce transformer oil and vacuum impregnate the insulation system. That results in a very oily core and coil set. And in either process, what happens in that vapor phase is everything shrinks. So when the core and coil come out of the vacuum chamber, the manufacturer has to tighten everything up, and this takes a fairly significant amount of people and time. So the alternative approach is to dry the insulation system and not vacuum impregnate it. In either case, the insulation material is going to reabsorb moisture when the unit comes out of the vacuum chamber. So this is an age-old question. In fact, I can remember going to a transformer manufacturer with a guy named Ron Barker, who was the transformer expert back then for Virginia Power. And we had an hour taxi ride, and that's what we talked about the whole way, whether or not it was better to oil impregnate the insulation system or not. Ron ended up putting in his specification that the insulation system had to be oiled in the vapor phase process. My personal opinion is it really doesn't matter as long as the manufacturer can demonstrate that he can put this unit back in the tank and fill it with oil quick enough so that the moisture doesn't reabsorb. And some manufacturers actually use what's called a desert room. So when they pull the unit out of the vapor phase system and they don't have it impregnated with oil, then they put it in a room that has very, very, very low humidity, somewhere down around 0.15 to 0.2% humidity. And then you have more time to be able to retighten everything up before it reabsorbs oil. So the key is, and actually I will, this doesn't answer the question, but I'm going to use this as an advertisement for this. So this brochure right here, C-grade technical brochure 637, condition of insulation in oil immersed transformers after factory acceptance test. This was just published last year, and it has a lot of guidance about exactly what we're talking about. So I guess, again, long answer to the question, but I don't think it matters as long as the manufacturer can demonstrate that the transformer insulation is less than 0.5% moisture content when it's leaving the factory.
Okay, thank you very much. And I assume these zero humidity rooms or very low humidity rooms, should I say, they're a very expensive option for processing a transformer, and that's why I haven't seen. Maybe with Siemens at some point, but yeah, I don't see those that frequently.
They're not only expensive, but they're also, the employees can only be in these rooms. I think the first one I saw was at Siemens in Europe, and I think it was 4 hours maximum that the employees could work in this room because it's so dry that it affects. They have to make sure that they're drinking water, and it dries out their body.
Okay. Yep. Interesting. I did have a couple of questions that came in just based on that I'll throw out there. Is there any recommended margin to ensure longevity? I'm assuming that's the margin post vapor phase or along those lines.
Yeah, I don't know. I mean, to me, longevity, it goes back to what I showed in the loading guide in IEC. Longevity is based on three things. One is temperature, obviously time, and then the acceleration factors, which is moisture and oxygen. So if I can maintain this transformer through its life and keep the moisture at a very low value, hopefully right around 0.5% as it was delivered, and then also keep it sealed, then you should have a very long life of your transformer. And most of transformer age is really less about that. It's more about the temperature part of that equation. And temperature is directly related to loading.
Yeah.
So, people talk about, well, these transformers last 50, 60, 100 years. That's probably because they're not loaded anywhere near their nameplate rating. So, if you want a transformer to last a long time, loaded at 50% of the nameplate, it should last hundreds of years.
Okay, and for those that have my mobile phone number, thanks for the feedback, and apologies if that question was totally out of context. I'm led to believe that we may have been referring to percentage margin for dielectric design, but thanks again, and I promise we'll do better next time. But we do need to keep moving a little bit, and I also can let you know that Weidmann have a technical article that we, as in Weidmann, we wrote a paper on the question of oil impregnate or not. So you can request that from your Weidmann contact or reach out to me, and I'll do my best to get that across to you. And there's also, I received a message saying that there is a rumor that in Germany, desert room employees get free beer. That's what I heard for working in those conditions, but that certainly can't be confirmed. You would have to find out about that yourself.
So there's also a discussion on this oiled versus non-oiled board and reabsorption. There's curves also in Transformer Board 3, as well as some other separate technical publications.
Okay, great. And by the way, thank you, everybody. Yes, we'll make the slides available. And yeah, to all those that have all my contact details, thanks very much. It's quite fun trying to balance text messages, WhatsApp messages, questions in the chat here. So I will try and get back to you, and I will try and get your questions thrown out there. But I apologize if I miss any of them. Tom, just moving on, we had a couple of questions on thermally upgraded paper, and I would appreciate fast answers on this because we want to try and get through a few more. So first of all, on thermally upgraded paper, how can I ensure my transformer has thermally upgraded cellulose insulation? I'm going to lead you straight in there, and I assume if you want to test the paper, it's a nitrogen content test, but also I guess the color of the paper, or there are a couple of simple and more complex options.
Okay, quickly, the first answer is that so thermally upgraded paper was introduced to the industry in early 60s. So if you have a transformer, and that allowed you to have what we call a 65 degrees C rise. So it allowed you to run the insulation hotter. So first answer is if your transformer is rated at 65 degrees C, then it should have thermally upgraded paper in it. In order to verify the paper itself, then you really need to take a sample of the paper, and any of the thermal upgrading systems that have been applied over the years are all based on nitrogen-based materials. So you measure the amount of nitrogen in the material, and if there's nitrogen between 1% and 2%, then you can be sure that your transformer paper is thermally upgraded.
Okay, thanks. I'm gonna keep moving here to try and get to a couple more. One that I know you've worked on both sides of the pond, I guess, with IEEE and IEC, and being very active on both, committees. Is there any future plan to align IEEE and IEC specifications, insulation specifications specifically?
So the insulation, I'm glad you said insulation. Your first question was specifications, and I would say, ooh, that's quite an effort. But specific on the transformer specification side, I don't see that happening. For quite a few years. There's a lot of effort to do what we call dual logo standards, where we have, for example, we just developed a dual logo standard for HVDC converter transformers because it's very specific application. In the case of insulating materials, IEEE does not write specifications for materials itself. IEEE more concentrates on the application. So in the world of North America, those material specifications would be developed by a committee called ASTM, American Society for Testing of Materials. So there's no, from what I'm aware of, there's no intention from IEEE to get into the material specification world. And in fact, I know us at Weidmann, we're incorporating and using the IEC material specifications globally. So those include North America as well. Yeah.
Okay. I am going to ask one question because I noticed that the Dupont guys were not that active, and we did have a question that related to Nomex. So a customer's asked, could Copaco paper be used close to the core or directly to the core? And what they typically use is Nomex 410 at the moment. And this will be interesting for me as I've never heard of Copaco paper.
So we call it Copaco.
Well, that's a good start. Thank you, Thomas.
Yeah, Copaco is it's a cellulose material. If you look at it, it's actually blue in color because it's made of cotton material, cotton threads that have been recycled from the garment industry, blue from blue jeans. Copaco is, because it's a cellulose material, it has the same thermal class as paper. So in the IEEE world, any material, insulation material that is going to be adjacent to the core has to be at least 130 degree material. So that's why Nomex, even though it's 180 plus, it's used because a cellulose-based material doesn't have adequate thermal capability for that application. So the answer is no, you couldn't use Copaco. You still have to use Nomex according to this need in the IEEE standards.
Okay, thank you. And just for those, I've had a couple of people raise their hand. You can, if you would like to ask a question, you need to type it into the question mark chat box. Unfortunately, there are too many of you out there for us to open up for a live Q&A. But if you type it in there, I promise I'll do my best to get to it. So I think I'm going to switch a little bit away now from those topics, Tom, and go into something that I know has been discussed a lot, and we have a lot of questions that have come up on this topic around alternative fluids and different things. So I want to lead you in here, Tom. So we had a question: are there any new developments in insulation technology, specifically with respect to renewable transformers and in relation to hydrogen formation? And I think the question, IDT, and again, forgive me if this is wrong, but I think that's industrial distribution transformers. So are there any new developments in insulation technology, specifically with respect to renewable and in relation to hydrogen formation in industrial transformers. So I'm guessing distribution size, maybe large distribution size. Forgive me if I've butchered your question there. I apologize.
No, I think I understand it, and I'm going to interpret it a certain way, and hopefully whoever asked the question, it's what I was interpreting. So I'm going to interpret it as the insulation system, and I know that there's an industry-wide problem over the last 10 years where these transformers for renewable applications have tended to have a lot of hydrogen generation. And the theory is that this is produced by partial discharges. And so one of the solutions that's been proposed has been to try using some of the alternative liquids that have higher hydrogen or higher partial discharge inception capability. I mean personally, I think that is a technology. The data that's been shown to demonstrate that has been on a couple of laboratory style tests. I think it's the theory behind it is I don't understand it, so I think it needs to be explored further before there's widespread acceptance of this technology. So I think partial discharge inception is a nature of the dielectric design of the insulation system, and that just by changing materials out with a retrofill application, for example, it's still open for question.
Okay. And I think that kind of answers or leads in. We had another question about specifically how effective it is to retrofit an oil-filled transformer with a natural ester fluid, for example. I think you touched on that there. But was there anything you missed out there for that?
Yeah, I'm going to point to another IEEE guide that's being developed. It's actually called IEEE C57.166. It's the maintenance guides for dielectric liquids. What we're doing is there used to be a guide for mineral oil, a guide for esters, a guide for synthetic esters, another one for silicone. We're combining all those together in one guide. And one thing that we're able to address by combining them all is the concept of retrofilling. And in that discussion, one of the things is, why are you doing the retrofill? One of the primary applications to use some of the alternative liquids over mineral oil is for fire point, what we call a K-class fluid. So anytime it's over a fire point over 300 degrees, then you can put this transformer in a building, or you don't have to build a firewall around it. It's very related to the insurance characteristics. So one way to get a low fire point is to retrofill a synthetic or a natural ester with a mineral oil. There's a lot of discussion in this guide, and it has to be followed how much residual oil there is, mineral oil, compared to how much of this higher fire point. And the value is typically 6 to 8% residual fluid, and that will tell you whether or not you get the right fire point. So one value of retrofilling is for a better fire point. Another point could be that you're retrofilling to improve the life of the insulation, the cellulose insulation. So there's been a lot of discussion, and there's annexes in the loading guide that say that a cellulose natural ester insulation system has a 10-degree higher thermal capability than a mineral oil cellulose system. So again, when you do a retrofill, you need to be careful about the residual mineral oil that's left in there, and then also how old that transformer is already before you do the retrofill. So to think that you can double the life of a transformer by retrofilling it. You could. It all depends on several factors. And then as far as dielectric strength, again, in my opinion, you don't gain anything from the dielectric standpoint. And in fact, um, for if it's a very large transformer, you need to consider some of these big oil gaps. And then I'll just say one thing to consider about retrofill is that these alternative liquids typically have a higher viscosity. They're thicker. So they'll have a poorer heat transfer capability. So you could have a thermal problem if you aren't looking at what the thermal design is. So if you have narrow oil ducts, for example, you might not be able to cool the winding the same way you did with a mineral oil. So they have a purpose. I think retrofilling is a good idea in a lot of cases. You just have to get some designers involved and know what you're doing. Just don't flatly retrofill and think that nothing, you don't have to think about any of these other parameters.
Okay.
Probably thought that was going to be a quick answer, huh?
Yeah, I did, but no, it's insightful, and thanks very much for running us through that. I am going to try now and just start to pull this together for the end, but we had one question that Thomas, pay close attention. I will try and answer it. So after introducing the vapor phase drying process, which ensures the extraction of maximum amount of moisture from the material, why is it necessary to use impregnated insulation materials? Well, just to prove, Tom, that I was listening to you this week, my understanding is that you don't have to use impregnated insulation materials if you are very quick to clamp down and tighten up that transformer when it comes out of the vapor phase to limit the amount of moisture that can re-enter the insulation system. If you impregnate the material, then it gives you a little bit more of a time buffer because it reduces the absorption of moisture through that impregnation. Is that right, Tom? Here's the test as to how well you did earlier this week.
Yes.
Good.
That's a quick answer. No, you're absolutely right.
Yep. And then somebody asked why Weidmann sometimes recommends the use of thermally upgraded materials in power transformers. And I wanted to get, I guess, such as Nomex. And I wanted to get to that one because you and I, a few years ago, spent some time on the road talking to utilities about Nomex material or aramid material in power transformers. So can you very quickly, Thomas, comment on why we as a company would potentially recommend for certain applications higher temperature materials in power transformers?
Very quickly? That's a hard one. I could go for an hour.
Just hit the applications, Tom.
Yeah. So higher temperature insulation materials allow you to get a higher power to weight ratio. And in many cases, the limit for loading a transformer is based on our material. The cellulose is the thermal limit to what you can load a transformer. And being able to use a high temperature insulation allows you to not have the solid insulation be the limit. Now it tends to be something else like auxiliary components, bushings, the insulating liquid. So it gives you a lot more flexibility. When you're looking at things like traction transformers, mobile transformers, transformers for wind farms, particularly offshore, that can be a tremendous advantage to be able to lower the weight of that transformer. So it gives you flexibility.
Okay. Thanks very much for that, Tom. I am going to close the live questions now there as we are very much running out of time as always, Tom. And I know many of you have no doubt meetings to run to after this. So I don't want to run out of time. I want one final question from the audience that came in. And this one, I like this one, Tom. It is, so you've had a long career, very long, and you've come to the end of it. If you were to start again, is there anything that you would do differently? And can you make any recommendations for the younger people in the audience who are maybe on the webinar that are interested to hear that? Or the old guys who want to know if it's the same
Yeah,
problem they had?
that's a hard one. Um, I think, I mean, early in my career, all I wanted to do was work. I wanted to get out of the education system as quickly as I could because I didn't really like school. But I kind of regret that. I think that learning more when I was young, because as you get older, that it's not just the capacity, but even the time to learn. So if any of you are younger here, a chance to get a master's degree or an MBA or something like that, for sure. Um, I don't know if it's as much as I regret over the long time, but something that I've enjoyed and that I um, probably wish I could have even done more of it was mentoring. Um, One of the things that we've done at Weidmann, it started with me as a college student, but then afterwards, when I became a manager and an officer in the company, we always kept an intern. We always tried to bring new people into the company, into the industry. As an industry, I think we're going to be challenged like crazy, and as a company, I know we are, to try to get enough people interested in our business and in our technology. I personally don't ever regret going into the transformer business. I think it's been rewarding. When I go to bed at night, I think about transformer problems, and when I'm in the shower, I think about them. And it's going to be kind of strange that I'm going to think about what kind of fish I'm going to catch the next day, or what kind of beer I'm going to make this weekend, and start thinking less about transformer stuff. But yeah, I don't know if that answered the question, but yeah,
I think it
it's
certainly
it.
touched on some key points there, Tom, about both your career and some of the the great things that you've achieved through, whether it be mentoring some of the younger engineers who are on the call today. And I'm sure I can speak on behalf of them and say that they're always very grateful for that mentorship and that leadership from a technical standpoint. And that's certainly a great achievement and a lasting legacy at Weidmann, that there are engineers in our organization that will continue the work that you've done, and maybe one day be in this same webinar as you, Thomas.
Oh,
You
I'm sure
mentioned,
they will be. I'm
yeah,
sure they
I
will
hope.
be. So,
And of course, you mentioned brewing beer. Are you designing some curves for your brewing time? And are you still going to be brewing those terrible IPAs, which I keep telling you are the easiest beers to brew and the worst tasting? But all you beer fanatics keep telling me that they're amazing, and I keep telling you it's harder to brew a lager than an IPA. Will you now brew me a lager more often now you have a bit more time?
I will brew more lagers as I have more time, but I'm never gonna stop with my IPAs. That's for sure. So just in reference, an IPA I can do start to finish in 3 weeks. A lager takes almost 3 months. So it's all in the planning. It's all in the planning.
Okay, well, good to hear though that you'll continue with the lagers. And of course, I'm sure while you're touring around, I know that you're moving again with your caravan, or what's the American term for the thing that you hitch to the back of
What
the
do we
car?
call it?
Travel trailer.
Travel trailer.
Travel trailer. You're
I
moving
call it
on.
I
I
call it
know.
a camper.
Yeah, you're moving on, and I can hear Rosie, your wife, in the background there, and I'm sure she'll be wondering why you're positioning your travel trailer next to various substations around the US, or with a view of the power lines and the transformers every morning. So I think it's also interesting just to give a special mention to the long-suffering Rosie Prevost, who's with you. Rosie, I'm not sure if you're there, but thank you for allowing us access to Tom for so long. Thank you for letting us sit in your basement bar drinking beer on an evening and discussing Transformers with colleagues for many, many years. You've certainly supported Tom, and it's great that now you have the time to spend with him. And thank you for giving him the time today and for the last week to put this together. I know your plan wasn't for the marketing team to be harassing Tom all week. So with that said, Tom, we've reached the end. Any final words? You have 30 seconds, maybe.
No, just goodbye. As many of you know, I'll still stay somewhat active in some of the standards groups and working for Weidmann to support them. So I don't think it's absolutely goodbye, but yeah, we're into a different phase. So
Excellent.
I
Okay.
think with that.
Yes, sorry, Thomas. Yeah, so hold on. I need to top my glasses, but it's I'm on a working day here, Tom, not the retirement party. So I can only have sparkling water. But thank you very much.
Sparkling water. Oh,
Yeah,
okay.
I know. It's been an absolute pleasure, and I sincerely thank you for the opportunity to work with you for the last 11 years, and we'll obviously keep in touch. And yeah, thanks very much again, and thank you to everybody for joining us. We will be back with more webinars. Don't worry, they don't disappear with Tom. And until next time, thank you very much for joining, and best wishes. Thank you. Bye-bye.
Cheers, everyone.
Cheers.
Cheers.